The armor disparity between German tanks and Allied infantry weapons represented a fundamental imbalance in combat capability. German Panzer III tanks entered service equipped with 50 mm of frontal armor protection. The Panzer IV medium tank featured 80 mm of hardened steel armor. When the Tiger I heavy tank appeared in combat operations during late 1942, it deployed with 100 mm of face-hardened armor, protecting the crew compartment and vital systems. Allied infantry possessed virtually no portable weapons capable of defeating these vehicles. The British Army's primary infantry anti-tank weapon was the Boy's anti-tank rifle, designated the Rifle Anti-Tank. 55 inches Boys. Under optimal testing conditions, this weapon could penetrate 21 mm of armor plating at 100 yards distance. Optimal conditions meant perpendicular impact angle, homogeneous armor steel, and laboratory-grade ammunition. Combat conditions never approximated these specifications. The weapon weighed 55 pounds, equal to the combined equipment load of 2 fully equipped soldiers. The recoil force was sufficient to cause clavicle fractures among operators. The weapon required a 2-man crew for tactical employment. Most critically, it could not reliably defeat anything more heavily armored than a light reconnaissance vehicle. American forces faced equivalent problems. When the United States Army entered combat operations, their designated infantry anti-tank weapon was the .50 caliber M2 Browning heavy machine gun. This same weapon was mounted on half-track vehicles and aircraft for suppressive fire missions. Against a moving Panzer IV tank, it provided approximately the same tactical effect as small arms fire. Some infantry units were issued sticky bombs, officially designated as adhesive grenades. Tactical employment required an infantryman to approach within arm-hess reach of an enemy tank and manually attach the explosive device to the vehicle's hull. Survival rates for soldiers attempting this maneuver were extremely low for predictable reasons. The British attempted deployment of the Projector Infantry Anti-Tank, abbreviated PIAT. This weapon launched a 2-pound bomb using a large compressed spring mechanism. Effective range was approximately 100 yards under ideal conditions. The weapon required 40 pounds of force to cock the firing mechanism and frequently failed to achieve armor penetration even when successfully striking the target. One British sergeant serving in North Africa characterized it in official reports as a drainpipe loaded with hope. The French Army employed the Brandt Model 1935 grenade launcher. Soviet forces used anti-tank grenades that required soldiers to close within throwing distance, approximately 20 to 30 yards, of enemy tanks equipped with multiple machine guns. These tactical requirements placed infantry in positions of extreme vulnerability. The strategic implications of this equipment disparity concerned Allied commanders at the highest levels. German tactical doctrine by 1941 emphasized combined arms operations. Panzer divisions attacked with tanks supported by mechanized infantry and mobile artillery, all coordinating movement and fire. When a German armored formation attacked a defensive position, Allied infantry could not simply establish static defenses and await their own tank support. Allied armor was frequently destroyed or forced to withdraw before reaching forward infantry positions. Allied forces required a weapon that a 19-year-old infantryman could carry, aim, and fire successfully before enemy machine gunners could engage him. The weapon needed to actually penetrate German armor plating and disable enemy tanks. By late 1941, after observing the destruction of entire divisions under German armored assault in France, North Africa, and the Soviet Union, Allied war departments received identical urgent requests from every theater of operations: provide portable weapons capable of destroying tanks, or prepare to lose the war one shattered infantry company at a time. Casualty statistics documented the crisis with devastating clarity. During the Battle of France in May-June 1940, German armor penetrated Allied defensive lines repeatedly and decisively, specifically because foot soldiers possess no effective counter to armored vehicles. The problem was not tactical skill or soldier courage. The problem was basic physics. Infantry weapons designed to penetrate 20 millimeters of armor could not defeat 80 millimeters of hardened steel plating. This was the operational situation facing United States Army Ordnance Department in early 1942. Solve this problem rapidly or begin explaining to American families why their sons died helpless against machines they could not damage. The solution emerged from two Army officers standing in a workshop in Maryland with a section of pipe and an unconventional idea. Captain Leslie Skinner had spent multiple months working on a handheld rocket-propelled grenade concept. The theoretical design involved a small explosive warhead projected by a solid fuel rocket motor that a soldier could theoretically throw farther than human arm strength permitted. The prototype functioned marginally, but the rocket motor's exhaust blast was sufficient to severely injure or kill the operator. This represented an unacceptable design flaw. Lieutenant Edward Ull observed one of Skinner's rocket test firings and posed the fundamental question: what if soldiers did not throw the rocket, but instead launched it from a tube? Skinner initially regarded this suggestion as impractical. Then both officers performed the necessary calculations. A simple steel tube, open at both ends, would allow the rocket motor's exhaust gases to vent backward while the projectile traveled forward. The operator would position himself behind the tube, aim at the target, fire the rocket, and if the design functioned properly, survive the launch sequence. The first prototype underwent testing in May 1942 at Aberdeen Proving Ground in Maryland. Ull obtained a section of pipe from available materials, measured it to match the rocket diameter, and sealed one end with a wooden plug containing a small aperture for the electrical firing wire. They mounted this assembly on a crude shoulder stock fabricated from wood and metal components. The complete weapon resembled improvised workshop equipment, which accurately described its origins. The first test shot traveled 60 yards and impacted within 10 feet of the aiming point. The second shot traveled 50 yards and deviated 15 feet to the left. The third shot tumbled end over end through its trajectory and landed 45 yards short of the target. However, three critical facts were established. The tube did not rupture or explode. The operator survived unharmed, and the rocket motor generated sufficient velocity to potentially damage armored vehicles. Army Ordnance observers watching from protected positions immediately recognized the tactical potential. General Gladian Barnes, Chief of Research and Development for Army Ordnance, observed the demonstration and immediately authorized continued development. By June 1942, the weapon received its official designation as the M1 rocket launcher. By July, soldiers began calling it the Bazooka after comedian Bob Burns' musical instrument of the same name. The unofficial name spread faster than official documentation could prevent. The problems began immediately. The M1 launched a 3.5-pound rocket with a shaped charge warhead designed to penetrate armor plating. Shaped charge munitions function through a specific physics phenomenon. An explosive charge lined with a copper cone focuses the detonation energy into a superheated jet of metallic plasma that penetrates steel armor like an oxyacetylene cutting torch. In theoretical testing, the M1's warhead could penetrate over 4 inches of armor plate. In practical field conditions, accuracy was extremely poor. At 50 yards, considered point-blank range in tank combat, the rocket might impact anywhere within a 20-foot circular area. At 100 yards, operators were essentially aiming in a general direction and hoping for favorable results. The problem was not the warhead design or the rocket motor performance. The problem was the smooth-bore launch tube. Without any stabilization mechanism, minor variations in rocket motor thrust or ambient wind conditions would cause the projectile to spin randomly during flight. Sometimes the rocket flew in a relatively straight trajectory. Sometimes it tumbled through the air. Sometimes it corkscrewed unpredictably, resembling the flight path of an intoxicated bird. Field testing conducted in late 1942 quantified the scope of the accuracy problem. Soldiers at Fort Benning, Georgia, fired multiple M1 rockets at stationary tank targets positioned at 100 yards distance. Hit probability was approximately 30% under ideal range conditions with no time pressure, no return fire, and stationary targets. In actual combat conditions with moving targets, enemy fire, and tactical stress, accuracy would decrease substantially below even these poor baseline figures. The situation generated serious concern among Army Ordnance officials and infantry commanders receiving the weapons. The bazooka concept offered genuine tactical potential, but a weapon with 30% hit probability at 100 yards was barely functional. Infantry commanders were not going to base their anti-tank tactics on a weapon system that missed its target 7 times out of 10. The accuracy problem required an immediate solution. The solution came from an unexpected source, a Swiss engineer working on shaped charge development who understood the physics of spin stabilization. Henry Mohaupt was born in Switzerland and established his career developing shaped charge technology for military applications. Shaped charges represented a revolutionary approach to defeating armor. Instead of relying on kinetic energy to punch through steel plating, shaped charges used explosive energy concentrated through geometric design. A cone-shaped metal liner, typically copper, was positioned in front of the explosive charge. When detonated, the explosive force collapsed the liner and transformed it into a superheated jet of metallic plasma, traveling at several thousand meters per second. This jet could penetrate armor steel far thicker than the warhead diameter itself. Mohaupt had developed shaped charge munitions for artillery shells and anti-tank projectiles throughout the 1930s. By 1942, he was working with the United States Army Ordnance Department on shaped charge applications for the Bazooka program. He understood the shaped charge warhead was not the problem. The problem was delivering that warhead to the target with sufficient accuracy to ensure tactical effectiveness. Mohaupt examined the M1 bazooka's smoothbore launch tube and immediately identified the fundamental flaw. The rocket projectile had no spin stabilization. Artillery shells and rifle bullets achieve accuracy through spin imparted by rifling, spiral grooves cut into the barrel. The spinning projectile acts as a gyroscope, maintaining stable flight orientation. Without spin, the bazooka rocket was aerodynamically unstable and vulnerable to any disturbance during flight. The conventional solution was to add stabilizing fins to the rocket. However, fins added weight, complexity, and manufacturing cost. They could also be damaged during handling or combat operations. Mohaupt proposed a different approach: cut rifling directly into the bazooka's launch tube, similar to a rifle barrel. The rifling would engage the rocket body and impart spin during launch. The spinning rocket would maintain stable flight, dramatically improving accuracy. Army Ordnance engineers raised immediate objections. Rifling was designed for solid projectiles like bullets and artillery shells, not for rockets with their own propulsion systems. The rifling would create friction during launch, potentially slowing the rocket and causing erratic ignition of the motor. The spinning motion might destabilize the rocket motor's exhaust flow, causing the rocket to veer off course. Rifling would significantly increase manufacturing complexity and cost. Most fundamentally, no one had ever successfully launched a rocket from a rifled tube. The concept violated established engineering principles for rocket weapons. Mohaupt countered these objections with physics. The rifling would only engage the rocket for a fraction of a second during the launch sequence while the rocket was inside the tube. Once the rocket exited the tube, the motor would continue providing thrust while the spin maintained flight stability. Any friction from rifling would be minimal compared to the rocket motor's total thrust. The manufacturing complexity was manageable, especially compared to producing thousands of inaccurate weapons that soldiers would not trust in combat. The debate continued for weeks. Some engineers supported Mohaupt's proposal. Others insisted rifling would create more problems than it solved. Finally, in January 1943, Army Ordnance authorized a test. They would manufacture a small number of rifled bazooka tubes, conduct controlled testing against the standard smoothbore version, and measure the accuracy difference. The test was scheduled for January 28, 1943, at Aberdeen Proving Ground. The results would determine whether rifling would be adopted or rejected for all future bazooka production. January 28, 1943, at Aberdeen Proving Ground in Maryland. The temperature was below freezing. Wind conditions were moderate. Army Ordnance had assembled 2 groups of bazooka launchers for comparative testing. One group consisted of standard M1 smoothbore launchers. The second group consisted of prototype launchers with rifling cut into the launch tube. Manufactured according to Mohaupt's specifications, the test protocol was straightforward. Both smoothbore and rifled launchers would fire at identical targets positioned at various ranges. Observers would measure hit probability, grouping size, and flight stability. The test would be conducted under controlled conditions to eliminate variables. Multiple firers would operate each weapon type to ensure individual shooter skill did not skew results. The smoothbore launchers fired first, establishing baseline performance. At 50 yards, hit probability against a stationary target was approximately 35%. At 100 yards, hit probability dropped to roughly 20%. At 150 yards, operators were essentially firing in the general direction of the target, with minimal expectation of hitting anything. The grouping patterns showed extreme dispersion. Rockets from the same launcher, fired consecutively, would impact several feet apart even at close range. Some rockets flew straight, others tumbled, others corkscrewed. The flight patterns were completely unpredictable. The rifled launchers fired next. The difference was immediately apparent to everyone observing the test. The rockets flew in straight, stable trajectories. At 50 yards, hit probability against the stationary target approached 80%. At 100 yards, hit probability remained above 60%. At 150 yards, the rifled launcher still achieved approximately 45% hits, better than the smoothbore launcher performed at half that distance. The grouping patterns were dramatically tighter. Multiple shots from the same rifled launcher would impact within a 1-foot circle at 50 yards. Even at 100 yards, the grouping remained manageable at roughly 2 feet. The rockets maintained stable flight orientation throughout their trajectory. The feared problems, friction-induced instability, motor interference, erratic flight, did not materialize. The rifling worked exactly as Mohaupt had predicted. The test data was unambiguous. Rifled bazookas were approximately 2.5 times more accurate than smoothbore versions at close range and more than 3 times more accurate at extended range. The improvement was not marginal or questionable. It was overwhelming and undeniable. Army Ordnance observers at Aberdeen understood the immediate implications. Every bazooka in production or deployed with troops was effectively obsolete. The weapon system that was supposed to give Allied infantry an effective anti-tank ability was delivering unacceptable combat performance. However, the solution now existed and had been proven under controlled testing conditions. Within days of the Aberdeen test, Army Ordnance issued new production specifications. All future bazooka launchers would be manufactured with rifled tubes. Existing smoothbore launchers in inventory would be retrofitted with rifled tube assemblies where feasible. Units deployed in combat theaters would receive rifled launchers on a priority basis. The changeover began immediately. The engineering specifications required rifling grooves approximately 1/16 inch deep, cut in a spiral pattern that completed 1 full rotation every 40 inches of barrel length. This was shallower and slower than rifle barrel rifling, appropriate for the larger, slower rocket projectile. The manufacturing process was adapted from existing rifling machinery used for artillery barrels and large caliber weapons. By March 1943, production facilities were transitioning to rifled manufacture. By June 1943, the majority of new bazookas rolling off assembly lines featured rifled tubes as standard equipment. These were the weapons that would deploy with American forces during the invasion of Sicily in July 1943 and subsequent operations throughout the Mediterranean and European theaters. Mohaupt's innovation had transformed the bazooka from a marginally effective weapon that commanders regarded with skepticism into a reliable infantry anti-tank weapon that soldiers could depend on in combat. The rifled bazooka would prove its worth in actual combat operations across every theater where American forces engaged enemy armor. The M9 rocket launcher, an improved version incorporating rifled tubes, better optical sights, and a two-piece tube design for easier transport, began reaching frontline units in summer 1943. These weapons participated in Operation Husky, the Allied invasion of Sicily in July 1943. American infantry divisions conducting amphibious assaults and inland operations encountered German and Italian armor throughout the Sicilian campaign. Bazooka teams reported significantly improved combat effectiveness compared to previous operations where smooth-bore launchers had been employed. The invasion of Italy at Salerno in September 1943 provided more substantial testing under intense combat conditions. The 36th Infantry Division landed on beaches under German observation and immediately came under counterattack by panzer formations. Bazooka teams positioned along the beachhead used rifled M9 launchers to engage German armor at close range. Lieutenant Colonel William Darby's Ranger battalions documented 11 confirmed tank kills using bazookas during the first 3 days of the Salerno operation. Combat reports from Italy documented numerous instances where bazooka teams defeated armor that would have been invulnerable to earlier infantry anti-tank weapons. At Monte Cassino, at Anzio, along the Gustav Line, during the advance toward Rome, rifled bazookas provided American infantry with the anti-armor capability they had desperately lacked during the early years of the war. June 6, 1944, D-Day. Every American infantry company landing at Utah Beach and Omaha Beach carried at least 4 two-man bazooka teams equipped with rifled M9 launchers. The weapons proved essential not only against German armor but also against fortified defensive positions where the shaped, charged jet could penetrate concrete gun emplacements and bunker walls. The Normandy hedgerow country presented ideal terrain for bazooka employment. The Bocage landscape featured small fields surrounded by thick earthen banks topped with dense vegetation, creating natural compartments that limited visibility and restricted vehicle movement. German defensive tactics involved positioning armor in ambush positions behind hedgerows, where they could engage Allied forces at very close range. The Ardennes Offensive in December 1944, commonly known as the Battle of the Bulge, tested every aspect of American infantry capability. German Panther and Tiger tanks penetrated American defensive lines in fog and snow. Isolated infantry units found themselves defending critical road junctions and towns, with bazookas as their primary anti-tank weapon. The 101st Airborne Division at Bastogne used M9 launchers to destroy at least 18 German tanks during the siege. By the time American forces crossed the Rhine River in March 1945, bazookas had accounted for over 800 confirmed German armor kills in the European theater. This figure, documented in after-action reports, represents only verified kills, not damaged vehicles or vehicles that withdrew after receiving bazooka hits. The actual impact on German armored operations was substantially higher. The 3.5-inch M20 Super Bazooka appeared in 1945, with rifling machined directly into the tube during manufacture. This weapon could penetrate 11 inches of armor, sufficient to defeat German King Tiger tanks from side angles. The M20 incorporated lessons learned from 3 years of combat operations with rifled bazookas, including improved sights, better mechanical design, and more reliable ignition systems. When North Korean T-34-85 tanks crossed the 38th parallel on June 25, 1950, American infantry units stopped them using M20 Super bazookas. These weapons existed because Henry Mohaupt had convinced skeptical Army Ordnance engineers that spinning rockets was worth the risk 7 years earlier. The M20's performance in Korea demonstrated that Mohaupt's innovation retained relevance beyond World War II. The fundamental physics of spin-stabilized projectiles remained unchanged. A rocket that spins flies straighter than a rocket that doesn't spin. This simple principle, proven at Aberdeen in January 1943, continued to validate itself in actual combat operations 7 years later. Henry Mohaupt never achieved fame for his contribution to infantry weapons development. Most soldiers who carried rifled bazookas through Europe never knew his name. He died in Switzerland in 1981. His obituary mentioned shaped charge development work, but nothing about the Aberdeen test that changed infantry warfare. Captain Leslie Skinner received a commendation for his bazooka development role and retired as a colonel in 1956. Official credit for rifled rocket launchers went to the United States Army Ordnance Department's innovation programs. However, every infantryman who fired a bazooka after January 28, 1943, benefited from one civilian engineer's willingness to challenge accepted doctrine with an idea that military engineers initially called reckless. The 800-plus confirmed tank kills in Europe, the 41 T-34s destroyed at Pusan, the countless engagements where infantry successfully defended against armor because they possessed reliable anti-tank weapons, all these outcomes trace back to rifling cut into a launch tube. The rifled bazooka stands as one of World War II's most significant yet underappreciated technical innovations. It transformed Allied infantry from helpless victims of German armor into soldiers who could fight back effectively. It provided tactical confidence based on weapon reliability. It established engineering principles that continue to guide infantry weapon development 8 decades later.